Next up on our list of approximation theorems, something known as Hurwitz's theorem. So remember that if you have x expressed as a regular continued fraction, the convergents Pn over Qn satisfy the following inequality. Not only is Pn over Qn close to x, but the distance is smaller than 1 over the denominator of the convergent we just used times the denominator of the next convergent q sub n plus 1. So as a corollary, we see that for any irrational number x, every convergent p over q satisfies that the distance from x to p over q is less than 1 over q squared, because this qn plus 1 is bigger than or equal to qn, so we would end up with this being less than 1 over qn times qn. So x minus a rational number less than 1 over denominator squared can be achieved infinitely many times for any irrational x and expressly by the convergence of the continued fraction. But can we do better? Can we guarantee that for an irrational x, there are rational numbers p over q so that that distance isn't just less than 1 over q squared, but less than something even smaller? Well, one thing we see is for any irrational x, there are infinitely many rational numbers p over q, so that the distance from x to p over q isn't just less than 1 over q squared, but actually less than half that. Observe, if there are infinitely many partial quotients bigger than or equal to 2, if you look at this inequality at the top, since qn plus 1 is an plus 1 qn plus something, that's bigger than an plus 1 qn. So this here is definitely less than 1 over an plus 1 times qn squared. So if an plus 1 is bigger than or equal to 2, we definitely end up with a less than 1 over 2 q squared here. But you can prove this theorem even if you don't know that there are partial quotients that are 2 or larger. So what we'll show is that if you take two consecutive convergents, at least one of them satisfies the inequality above. So let's suppose that we have an irrational x, and our aim is to show that out of two consecutive convergents, Pn over Qn and Pn plus 1 over Qn plus 1, at least one of them satisfies that the distance from x to the convergent isn't just less than 1 over the denominator squared, but 1 over 2 times the denominator squared. We want to show that one of these holds. If out of any two consecutive convergents, at least one of them satisfies this inequality, then for any irrational x, it will be satisfied infinitely many times. Well, let's assume to the contrary that both of them fail. We know we can't have equality because x is irrational, although it's not a huge issue. X is irrational, so we cannot possibly have equality, so if we assume it's not less, then it must be more. Okay. Now we know the distance from two consecutive convergents is 1 over the product of the two denominators. But if we simply add these two expressions together, one of them is positive and one of them is negative, because remember, the convergents are on alternating sides of x. So when I add them together, in absolute value, you will just get Pn over Qn minus Pn plus 1 over Qn minus 1, or maybe in the opposite order, but whatever, it's inside an absolute value. So because these are of opposite sign, when I add them together in absolute value, I can just cancel out the x's. One of them will have a plus and one will have a minus. This is exactly equal to 1 over the product of the two denominators, but on the other side, we'll have bigger than this plus that, and I've gone ahead and factored out the 2. Okay, so if it fails for two consecutive convergents, we'll end up with 1 over Qn times Qn plus 1 is bigger than this, which once we give it a common denominator works out to this fraction right here. But now we can cancel a Qn and a Qn plus 1 out of both sides. And we end up with 2 times Qn plus 1 is bigger than Qn squared plus Qn plus 1 squared. If I subtract the two Qn plus 1 over to the other side, this actually factors quite nicely, and we end up seeing that 0 is larger than the square of something, in fact, the square of an integer. That certainly cannot happen. So between any two consecutive Pn over Qn, at least one of them satisfies the inequality of the theorem, and therefore for any irrational x, it is satisfied infinitely many times. So recall that we've actually shown before that convergents Pn over Qn are exactly the best approximations of the second kind, with the possible exception of P1 over Q1. Specifically, if you take any rational number a over b, whose denominator is less than Qn, the distance of bx to the integer a has to be bigger than the distance of Qnx to the integer Pn. So the following is immediate, but we haven't formally stated it. If a over b is a rational number and bx minus a, an absolute value, is less than qnx minus pn, then b has to be bigger than or equal to qn plus 1. So whatever a over b exists with a minimal denominator, suppose there are lots of a over b's that satisfy this, then there is a smallest denominator for which it happens. That next a over b would have to be a best approximation of the second kind, but the best approximations of the second kind are exactly the convergents. Therefore, the smallest denominator you can possibly have after qn for a best approximation of the second kind is qn plus 1. So any denominator you see after qn must be at least as big as qn plus 1. All right, so we established that out of two consecutive convergents, at least one of them, p over q, satisfies that the absolute value of x minus p over q is less than 1 over 2q squared. Now suppose that x is irrational and p over q is a rational number that satisfies that inequality. Well, out of any two consecutive convergents, at least one of them must satisfy this inequality, but what we're about to prove is that the only rational numbers that can possibly satisfy this inequality are the convergents. Let's suppose you have a rational number that satisfies this inequality. The denominator of this arbitrary rational number q lies in between two consecutive denominators of the convergence. Qn is less than or equal to q is less than qn plus 1. Q is less than qn plus 1, and p over q is not pn over qn. So by the previous corollary, we see that the distance of qx to p has to be bigger than or equal to the distance qnx to pn, because pn over qn is a best approximation of the second kind. Any next best approximation of the second kind that makes that distance smaller has to have denominator at least qn plus 1, and this rational number here does not. Therefore, this rational number p over q is not a best approximation of the second kind. Now, x minus p over q is less than 1 over 2q squared. That was our initial assumption about our rational number p over q. Therefore, we find that 1 over 2q, if we simply multiply this by q on both sides, is bigger than qx minus p, but qx minus p is bigger than or equal to qnx minus pn. So we see that 1 over 2q is larger than qnx minus pn. If we divide both sides by qn, we end up with the following. So having assumed that p over q is not a convergent, but does satisfy the inequality of the theorem, we found for the specific choice of qn, so that qn is less than or equal to q is less than qn plus 1, we have the inequality 1 over 2 times q, the denominator of the rational number we started with in the theorem, times qn, the largest convergent that isn't bigger than q, is bigger than the distance from x to pn over qn. Now p over q is not equal to pn over qn. Therefore, p times qn minus pn times q cannot be 0. But it's an integer, so in absolute value, if it's not 0, it's at least as big as 1. Therefore, that quantity, whatever it is, over q times qn is bigger than or equal to 1 over q times qn. And therefore, that's the distance of p over q to pn over qn. So the distance from p over q, the rational number we assumed satisfies the conditions of the theorem, to the convergent pn over qn, the last convergent whose denominator is not larger than q, must be bigger than or equal to 1 over q times qn. So under the assumption that p over q satisfies our theorem, isn't a convergent, and we picked n to be the index of the convergence so that the denominator qn is less than or equal to q is strictly less than qn plus 1, we've got two separate inequalities we've established. First, the distance of x to this convergent is less than 1 over 2q qn, but the distance of p over q to that convergent is bigger than or equal to 1 over q qn. Now in that second inequality, we're going to insert a plus x minus x and break it apart using the triangle inequality. So this is flat out equal to this right here. We just did a minus x plus x. However, this right here is less than or equal to this absolute value plus this one. So putting this less than or equal to that sum, overall we have this sum is bigger than or equal to 1 over q times qn. And observe that here, p over q minus x in absolute value we assumed is less than 1 over 2q squared, and the distance from x to pn over qn we already derived is less than 1 over 2q qn. Okay, so we go ahead and substitute that this is less than that. Again, we're just building less than in this direction. And therefore we find that the distance of p over q to x is in fact bigger than or equal to this minus that. I have 1 over qn minus a half of it, so 1 over 2 qn is what remains here, but qn is less than or equal to q, therefore this is bigger than or equal to 1 over q squared. So p over q minus x in distance must be bigger than or equal to 1 over 2q squared, but that exactly contradicts the assumption that it was less than 1 over 2q squared. So what we've proved is that if p over q is a rational number that satisfies the inequality of the theorem, it must be one of the convergents of x. So only convergence can possibly satisfy that inequality. Not every convergent does, but at least 1 out of every 2 does. So can we do any better? Every other convergent must satisfy, and when I say every other, I don't mean in a strict sense. I mean out of any consecutive pair, at least one of them satisfies this inequality. But only convergence can possibly satisfy that inequality. So if we're looking to do any better, we are definitely only looking at convergence. Can we actually do any better? Can I replace the 2 with anything bigger? Well, we know the following. The distance of x to the convergent is less than 1 over an plus 1 qn squared. However, we've established this in the past, and from here, setting up that qn plus 1 is an plus 1 qn plus qn minus 1, and using the inequality that qn is bigger than qn minus 1, you'll end up with this. So the distance from x to this convergent is smaller than 1 over an plus 1 qn squared, but bigger than 1 over an plus 1 plus 2 qn squared. And remember, if we're looking to do better than this approximation, we have to be restricted to convergence. But the convergents don't do that well. So the closeness of the approximation isn't that good. Okay? Whatever an plus 1 is, it really tightly controls just how good this approximation can be. So for example, we cannot expect that for every irrational x, we will have infinitely many p over q, that the distance from x to p over q is less than 1 over 3 q squared. If every single a sub I is equal to 1, then every convergent is bigger than 1 over 3 qn squared away, and only convergence could possibly satisfy this inequality because they're the only ones that can satisfy this one. So having a 2q squared in the denominator can be achieved by infinitely many convergents. Having a 3 in the denominator might not be. So what's the exact cutoff? Somewhere between 2 and 3, is there a number that can be achieved infinitely many times for any irrational number, but larger values can't? Well, here's what Hurwitz's theorem says precisely. For any irrational x, there are infinitely many rational numbers p over q, so that the distance of x to p over q is less than 1 over the square root of 5 times q squared. But also, if you tried to put something larger than root 5 down there, you can find an irrational x for which there are only finitely many rational numbers satisfying this inequality. So specifically, putting a root 5 here, there will be infinitely many rationals for any irrational x. However, if you tried to put something larger than root 5, we're going to find a specific x for which this only happens finitely many times. And that second half is actually easier to prove. Just start off with x being the continued fraction whose partial quotients are all 1. We've already seen that larger partial quotients allow you to achieve tighter error estimates here. So let's assume the partial quotients are as small as possible. They are all 1. Okay, so x is equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over 1, etc. And we've already established that this sort of freehand arithmetic is fine. Here we have exactly the expression x we started with. So x is equal to 1 plus 1 over x. Multiplying both sides by x and moving some things over, we get x is 1 plus or minus root 5 over 2. But x is certainly positive, therefore it's 1 plus root 5 over 2, which is the golden ratio phi. So what we've done is we've established that 1, 1, 1, 1, 1, etc. is the continued fraction expansion of the golden ratio or golden mean phi 1 plus root 5 over 2. So we have our continued fraction expansion of the golden mean. The Pn over Qn, the convergents, take a particularly interesting and nice form. Now remember, our goal here in Hurwitz's theorem is to compare x to a rational number p over q and show that that's less in absolute value than 1 over a constant times q squared, where that constant is root 5 or maybe something bigger. But we've already shown that if you put a number larger than 2 in there, the only possible rational numbers that could possibly satisfy it are convergents. So we really only have to look at the convergence of our number in order to try to establish this theorem. So the convergence Pn over Qn, the p's start with a 1 and then a 2. And then because every partial quotient is equal to 1, this recursive formula just boils down to the next p is the sum of the two before it. The q starts with a 1 and a 1 and then has the same recursive formula. So both of them say the next term is the sum of the two before. This starts with a 1 and a 2, this starts with a 1 and a 1. So that's the same recursive formula as the Fibonacci numbers. And both the p's and q's start with two consecutive Fibonacci numbers. 1 and 2 are consecutive Fibonacci numbers, as are 1 and 1. Therefore, the p's and q's are Fibonacci numbers, fn plus 2 and fn plus 1 specifically. So there's a well-known explicit formula for the Fibonacci numbers. Fn is 1 over root 5 times phi to the n minus phi bar to the n, where phi is the golden mean 1 plus root 5 over 2, and phi bar is its algebraic conjugate 1 minus root 5 over 2. So Pn is a Fibonacci number, and here is its Benet's formula representation, and Qn is also a Fibonacci number. So we can compute this distance, Qn, times Qn phi minus Pn. Okay, now the point here is that for Qn phi, now Qn is just this expression right here. Pn also has a 1 over root 5, and Qn here has another 1 over root 5. So after factoring all that out, we just have a 1/5. Here's the numerator from the Qn, and here's Qn phi minus Pn, once the numerators have all been simplified. Now inside the absolute value here, we multiply some stuff out. We get phi to the n plus 2 minus phi to the n plus 2. Those cancel. A minus phi bar to the n plus 1 times phi. Here's a minus phi bar to the n plus 1 times phi. And a plus phi bar to the n plus 2. So that's there. With this expression for phi and this for phi bar, you can check that phi bar minus phi is exactly minus root 5. So that's what's going to happen right there. So I'm going to take that minus root 5 in absolute value and factor it out. So this becomes a 1 over root 5. So now what we have is 1 over root 5. If I take this parenthetical term and distribute it back into the absolute value, we get phi times phi bar to the n plus 1. And here we get a phi bar to the n plus 1 plus n plus 1, or 2n plus 2. The notation's a little confusing. This is not phi to a negative power. This is phi bar to the power n plus 2. So for every n, Qn times the distance from Qn phi to the integer Pn is given by this expression that we've derived. But inside the absolute value, phi times phi bar, 1 plus root 5 over 2 times 1 minus root 5 over 2, is exactly minus 1. So inside this parenthesis, we just have a minus 1. Also, the absolute value of phi bar, 1 minus root 5 over 2, is less than 1. And so we're taking higher and higher powers of it. So when I take Qn times the distance of Qn phi to Pn, this just becomes a minus 1, and this is something less than 1 in absolute value. Now what happens when you take something smaller than 1 in absolute value and you raise it to larger and larger powers? It collapses down to 0. So in the absolute value here, you have a plus or minus 1 and a vanishingly small term that you're adding or subtracting. If we take a limit as n goes to infinity, that absolute value just goes to 1, and we get 1 over root 5. From which it follows, if this sequence has limit 1 over root 5, if you pick any alpha bigger than root 5, there will only be finitely many terms for which this inequality can possibly hold. If you multiply the Qn squared to the other side, you'll get exactly this. Okay, and if alpha is bigger than root 5, here I have something less than 1 over root 5. If the limit is 1 over root 5, only finitely many of them could be less than something which is less than 1 over root 5. So thanks to our knowledge of how sequences converge and some elementary real analysis, for specifically the golden ratio phi, if you pick any alpha larger than root 5, there can be only finitely many convergents that satisfy this inequality right here. So we have shown that if you attempt to use any alpha larger than root 5 in the inequality of this theorem, the specific number of the golden ratio will only satisfy it finitely many times. So we're going to set aside the question about, just because I found one violation, what does that tell me about most numbers? The reason we're setting this aside is because you can actually say something about this, but you have to define what you mean by most numbers, because the set of numbers we're looking at, irrationals, is a very infinite set. So what does most actually mean? Also, the way I would think to do it relies on establishing far more techniques than I really want to get into. So the statement of this theorem is, for every irrational x, can you satisfy this inequality infinitely many times? And since there is one specific irrational number for which any choice of alpha larger than root 5 gives an inequality that is satisfied only finitely many times, for any number larger than root 5, the answer is no. It cannot be done infinitely many times for every irrational number. So now let's look at the other half of the theorem. If you go ahead and plug exactly root 5 in for alpha, for any irrational x, we need to prove there are infinitely many rationals that will satisfy the inequality. So we're going to use a technique fairly similar to how we proved it for the case of alpha equals 2. Back then we said for any 2 consecutive convergents, at least one of them will satisfy the inequality. We're now going to show for any 3 consecutive convergents, at least one of them satisfies the desired inequality. So let's assume to the contrary that all of them happen to fail. Specifically, we're assuming that we have our irrational x, and for some n we have 3 consecutive convergents, so that the distance of x to the convergent is bigger than or equal to 1 over root 5 times its denominator squared. The first thing we're going to establish is that the partial quotient an plus 1 has to equal 1 if all 3 of these things hold. Now, each inequality on its own actually tells us quite a lot. This quantity here is definitely less than 1 over qn times qn minus 1, but qn is at least as large as an times qn minus 1. So this is definitely less than 1 over an times qn minus 1 squared. If we're bigger than or equal to 1 over root 5 times qn minus 1 squared, this tells us that an is less than or equal to root 5. Similarly, this tells us that an plus 1 is less than or equal to root 5, and this tells us that an plus 2 is less than or equal to root 5. But the partial quotients have to be positive integers, so if they're less than or equal to root 5, they have to be either 1 or 2. Now our goal is to show an plus 1 is 1, and we've established that all of these partial quotients are either 1 or 2. So let's just look at that middle inequality. On the one hand, we've assumed that the distance of x to Pn over Qn is bigger than or equal to 1 over root 5 times Qn squared, but we already know it's less than 1 over the product of those two consecutive denominators. So ignore the middle, cross-multiply, cancel a Qn. Qn plus 1 must be smaller than root 5 times Qn. Recursive formula for Qn plus 1, we plug that in, and now we do the same for the Qn's that we have. Now if we were to distribute everything out, every term either has a Qn minus 1 or a Qn minus 2, but not both. So we're going to take all of the Qn minus 1 terms, move them to the left, all of the Qn minus 2 terms, move them to the right, and factor. And you'll establish this, that Qn minus 1 times this parenthetical quantity must be less than Qn minus 2 times this one. Now an plus 1, we're hoping to show that it's equal to 1, but we already know it's either 1 or 2. So let's assume to the contrary that it's 2. Then I look at this expression and I plug in an plus 1 equals 2. So Qn times this must be less than or equal to Qn minus 2 times this. But this is Qn minus 1 times a quantity, and now I'm smaller than or equal to Qn minus 2 times a quantity, but this Q is bigger than this one. So the thing I'm multiplying it by must be smaller than what I'm multiplying this by. Okay, so 1 plus an times 2 minus root 5 must be less than root 5 minus 2. If you manipulate this for the quantity an, noting that 2 minus root 5 is negative, so when you divide by it, you'll end up flipping some things around, this reduces to an is bigger than the quantity 3 minus root 5 over root 5 minus 2, which is larger than 3, which is definitely larger than root 5, contradicting our existing knowledge that an is less than or equal to root 5. So an plus 1 cannot equal 2, so it must equal 1. So we've assumed for our irrational x, we have 3 consecutive inequalities like this. This is to the contrary of Hurwitz's theorem, that these 3 consecutive convergents failed to be less than 1 over root 5 times the denominator squared. Now let's take a look at what's inside the absolute values. Remember that the convergents are on opposite sides of x. One is bigger, one is less, then the next is bigger, and so forth. So perhaps x was bigger than this one, but then x would be less than this. So if I drop the absolute value, I should actually have Pn over Qn minus x, but then this one would be fine. Or the other way around. This one should get flipped, this one is fine, and then this one should get flipped. Either way, two consecutive ones here have a plus x and a minus x. And then if you add them together, you can cancel those x's out. So I don't actually know which of these are positive and which are negative, but because they alternate, if I drop the absolute value and add them and then reimpose an absolute value, because maybe these were supposed to be in the opposite order, we'll end up with getting rid of the x's and comparing two consecutive convergents to each other. But we know this distance is 1 over the product of their denominators, and on the other side of the inequality sign, you simply get a 1 over root 5 that you can factor out, and then you have the sum of the reciprocals of the squares of the denominator. But you can do the same thing with the second two inequalities to get the same looking thing, but with all our indices shifted up by 1. With a little bit of algebraic manipulation, ignoring the term in the middle and just focusing on the left and right, you can manipulate them to look like this. The first becomes qn minus 1 times root 5 is bigger than or equal to the sum of those squares, whereas the second becomes qn plus 1 times qn times root 5 is bigger than or equal to the sum of those two squares. If we then add these inequalities together, we can factor a qn root 5 out of the left, and on the right we have two qn squareds, but otherwise we have qn minus 1 squared and qn plus 1 squared. But remember, we've established that an plus 1 is 1. That means qn plus 1 is an plus 1 qn plus qn minus 1. That's just qn plus qn minus 1. And here, similarly, this is a qn plus qn minus 1 that we will then square. Once we make that substitution, square the one on the right, and collect like terms, we have the following inequality. Okay, the utility here is there are no longer 3 consecutive indices, just 2. We have qn's and we have qn minus 1's floating around. So under our original assumption that for 3 consecutive indices, the convergents were further away from x than 1 over root 5 times the denominator squared, the first thing we did was show that the partial quotient an plus 1 had to equal 1. Then using that fact, we got this nice little algebraic expression. Okay, if we move everything over to one side, we have some qn minus 1 squareds, we have some qn times qn minus 1s, and we have some qn squareds. It's a nifty little factoring trick, but you can verify that indeed this expression here is exactly 1/2 times this squared. But observe, I now have 0 is bigger than or equal to 1/2 times something squared. That means the thing being squared had to equal 0. So if 2qn minus 1 plus 1 minus root 5 qn has to equal 0, you can solve this to get that qn over qn minus 1 must be 2 over root 5 minus 1. That's a contradiction because qn is an integer, qn minus 1 is an integer, and root 5 is not a rational number. Okay, you could now solve this expression for root 5 and you'd have nothing but integers on the other side. So since root 5 is irrational, qn over qn minus 1 can't be equal to 2 over root 5 minus 1. That means that this expression cannot equal 0, and so forth and so forth and so forth. We cannot have 3 consecutive convergents, all failing to be closer than 1 over root 5 times the denominator squared to x. Therefore, out of 3 consecutive convergents for any irrational number x, at least one of them satisfies that x minus p over q is less than 1 over root 5 times q squared. So for every irrational x, that inequality can be achieved infinitely many times. Hurwitz's theorem is complete. For any irrational x, x minus p over q less than 1 over root 5 times q squared can be achieved infinitely many times. However, if you pick any number larger than root 5, call it alpha, x minus p over q less than 1 over alpha times q squared can only be achieved finitely many times for a certain specific irrational number and therefore cannot be achieved infinitely many times for every irrational number. So in summary, the convergents of x always satisfy this nice chain of inequalities. The distance of x to the convergent Pn over Qn is always less than 1 over the next partial quotient an plus 1 times the denominator Qn squared. One thing we've done with this is that computing the convergent Pn over Qn directly before the appearance of a large partial quotient an plus 1 gives a very good approximation to x. In the previous video, for example, The fact that the continued fraction expansion for pi has a single very large partial quotient that appears fairly early in its expansion gives us a rational number with relatively small denominator that is really close to pi. But a natural question to ask then is, if the ANs are small, and I can't necessarily rely on this being big, is there another reason why I might be able to put a number there and get the same type of estimate? So what's the largest value of alpha for which x minus p over q less than 1 over alpha q squared has infinitely many solutions, regardless of which irrational x I pick? This inequality up here tells me that for certain specific irrationals that have very large partial quotients in them, I can get really big numbers down here. But what will work no matter what, even if the ANs are small? It turned out to be relatively straightforward to show that plugging in alpha equals 2 does have infinitely many solutions for every irrational, but alpha equals 3 doesn't. Hurwitz's theorem gives an optimal constant to put there, root 5. The golden ratio, if you let alpha be bigger than root 5, will only have finitely many solutions. So if our goal is to find infinitely many solutions for every irrational, anything bigger than root 5 isn't going to work. But we did show that for any irrational number, out of any 3 consecutive convergents, at least one of them will satisfy that inequality when alpha equals root 5. Therefore, it will have infinitely many solutions. This is a precise cutoff kind of result. Alpha equals root 5 or smaller? Yes, infinitely many solutions no matter what. Alpha bigger than root 5? No, not necessarily. It's not exceptionally common to get such a precise cutoff like this in a mathematical theorem. So Hurwitz's theorem is really quite nice in that regard. Also, we're not attempting to address, for values of alpha larger than root 5, some irrationals fail, but how many? Which ones? We're not trying to answer that question. It just takes a lot more work, and we're already just over half an hour.